All right, so today we're going to finish up our strong acid pH calculations, and then we're going to go and discuss how to do it for weak acids. So, as a recap for what we were talking about in the last video, all right, we were calculating our pH for strong acids, so our procedure was to ask ourselves, is it strong? If it is, then we write our dissociation reaction. We're going to convert our moles of the compound we start with to, we're going to convert our concentration of the compound we started with to our concentration of H+, and then we're going to calculate our pH by the negative log base 10 of our concentration in H+. All right, now, we also discussed how you calculate POH and concentration of OH, but we didn't get a chance to do an example of that. So I'm going to show you how to calculate all of these different properties for a strong acid. So if, for example, our concentration of H+ is found to be 5.4 times 10 to the negative 5th molar, let's first calculate our pH. We know that pH is equal to the negative log base 10 of our concentration of H+. All right, so plugging that in, right, we will take the negative log base 10 of 5.4 times 10 to the negative 5th molar, right? And that will give us, since we have two significant figures, we're going to have two decimal places, right? Once we get this, this will be 4.27. Again, making sure that I have two decimal places after. So that would be how we get our pH, 4.27. All right? Now, once we have our pH, it's very easy to calculate our POH, right? Because we know that the pH plus the POH is equal to 14, okay? So that means that if I want to calculate my POH, all right, an easy way to do that is to say, okay, well, I take 14, I subtract off my pH, okay? So that means that it will be 14 minus my 4.27 that I just found, okay, which means that my POH is equal to 9.73. All right, so that would be my POH. Very easy, okay, especially if we've already got our pH. Now, we talked about how the pH is equal to the negative log base 10 of our concentration in H+. We also know that our POH is equal to the negative log base 10 of our concentration in OH minus, right? Remember that the P, right, our potence or power, is just going to say, okay, I take the log base 10 of that concentration. Well, if I want to get my concentration, we learned this in algebra, right, that we can take 10 as our base of both sides, okay? So that would give us, that would mean that our concentration in OH minus is equal to 10 to the negative concentration, 10 to the negative POH. All right? If I wanted the pH, if I wanted the concentration of H+ and I only had the pH, it would be 10 to the negative pH. Okay? If I wanted to know my Ka, right, and I had my pKa, it would be 10 to the negative pKa. All right? So you can use this form to always get your concentration or whatever was inside of your logarithm, right? Just like what you guys did in algebra, right? So we know our POH, right? So all I have to do is say that it's 10 to the negative POH, which is negative 9.73, right? So that means that my concentration of OH minus is equal to 1.86 times 10 to the negative 10 molar. Okay? So that should be pretty straightforward. All right, now, before I go on, I wanted to give you guys another quick example of doing that last logarithm change, right? Where we undo the logarithm. So as another example, let's say that I want you to convert a pH equal to 5.2, like I give you that, and I want the concentration of H plus, okay? If my pH is 5.2, my concentration of H plus is going to be equal to 10 to my negative pH, which is equal to 10 to the negative 5.2, where I've just plugged in my pH there, all right? Which means that my concentration of H plus is equal to 6.31 times 10 to the negative 6 molar, okay? Another example, right, would be, let's say that I give you a pOH equals 9.7, right? What's your concentration in OH minus? Well, all you have to do is say, okay, well, I want my concentration in OH minus. I know that that is going to be equal to 10 to the negative pOH, all right, which is equal to 10 to the negative 9.7, which is equal to 2.00 times 10 to the negative 10th molar. All right, so not super bad. All right, now, the next thing that I want to talk about is how to calculate a pH of a weak acid. All right, so again, we always start our question for acids by asking if it's strong, right? So is it a strong acid? Well, let's say that we are doing it for hydrofluoric acid, right? Is it a strong acid? Oh, no. Then we would compare our Kas for the acid. So we'd look up the acid Ka in a table, and we would compare that to the Ka for water. All right. Then we would write the reaction with the bigger Ka. If the bigger Ka is for the acid, we would write down the acid reaction. If it's for the water, we would write down the water dissociation reaction. All right. Because we want to know which one is going to produce more H plus in solution, okay? And since it's a weak acid, it may actually be the water, okay? So we have to compare those. Then we're going to build an ice table. We're going to write the Ka expression after we've done our ice table using our equilibrium row. That was our E row in our ice table. We're going to use that to calculate the value of X, right? Because we're going to have an X in our table, right? Then once we've got our X, we're going to get our concentration in H plus, and then going to calculate our pH. Okay, so let's walk through an example. This is listed on slide 21. All right, now let's say that we have a 1.00 molar solution of hydrofluoric acid, and it has a Ka of 7.2 times 10 to the negative 4. So our first question to ask is it a strong acid? Answer for hydrofluoric acid is no. All right, now, since it is not a strong acid, okay, so since we have a weak acid, we need to determine which species produces the most H plus. All right, so again, this is where that comparison of Kas is going to be important. Okay, so in step 2, right, we're going to compare our Kas. Right? So we have the hydrofluoric acid dissociation, where we take hydrofluoric acid, it forms an equilibrium with H plus and F minus, right? It has a Ka equal to 7.2 times 10 to the negative 4th, right? We got that in our problem statement. And then we have our water dissociation, where we take H2O, it forms an equilibrium with H plus and OH minus. Okay, now if you remember, water has a Kw equal to 1.0 times 10 to the negative 14th. Okay, that means that our Ka for the hydrofluoric acid is bigger than that of the H2O. Okay, so this one is bigger. All right, so we're going to write our reaction for the bigger Ka. I'm going to save that step and just say, okay, well, I already wrote it here. All right. Then in step 4, right, that would be step 3. Step 4 would be to build our ice table. Okay. The way that we do that, we first are going to write our reaction, HF. We know that it favors the left. We have H plus and F minus, right? We have I, C, E. So we had our reaction. In our initial row, okay, what are we going to have? Well, we know that we have a 1 molar solution of HF, so we know our concentration for HF, that's 1.00 molar. All right, and we're assuming that it starts all together. Okay, so that means that we have none of this and none of this, right? We didn't say anything about it, so that means that those are going to be 0, just like we've done before. Then we're going to have our change row, right, which was our stoichiometric coefficient times our change, right? And remember, it was plus for products and minus for reactants, okay? So here we have our stoichiometric coefficient of 1 times negative x because it's a reactant. This is now a product, right? Because it's to the right side of the arrows. So this is a stoichiometric coefficient of 1 times a positive x because it's a product, a 1 times positive x because it's a product. All right? Then lastly, we add them up. Okay? So we have 1 minus x, we have 0 plus x, and we have 0 plus x. Okay? In step 5, what are we going to do? We're going to write our Ka expression using our equilibrium row in our ice table, and then we're going to calculate x. All right? So we have that Ka is equal to x squared over 1 minus x, right? Because I have, if I were to write it, it would look initially like my concentration in H plus to the first, my concentration in F minus to the first, all over my concentration in HF to the first. All right, so it would basically be x times x all over 1 minus x, which is x squared over 1 minus x. Okay, now I know that that is equal to 7.2 times 10 to the negative 4th. All right, now I can solve this one of 2 ways. All right, I can either solve it by using my quadratic equation. Okay, this will always work. All right, if your numbers are done correctly. All right, now, or I can use the 5% rule. All right, now, basically what the 5% rule is, it says that since x is likely very small, okay, and by that I mean x is likely much, much smaller than 1, okay, what we can do is we can drop the x only in the denominator. Okay, so notice how we have this little x here. Okay, since x is likely small, we can probably drop that x. Okay, but if we do that, we have to check. Okay, so what we can do is we can say Ka, it was equal to x squared over 1 minus x. If we drop that x in the denominator, right, it will become approximately equal to x squared over 1, which is equal to x squared, which says that x squared is 7.2 times 10 to the negative 4th. That makes it very easy for us to calculate x because it's just going to be the square root of this, okay, which is 0.0267. Okay? Now, as I said, if you do the 5% rule, you have to check. Well, how do we check it? What we're going to do to check is we're going to take our X that we got and we're going to put it over our initial concentration. Okay? And then we're going to multiply it by 100. Okay? So that would mean that I'm going to take my value of X, which was 0.0268, right? That's my X. And I'm going to put it over my initial concentration of 1.00 molar. And I'm going to multiply that by 100, which is going to give me 2.68%. If that is less than 5%, then you're good. Okay? Otherwise, you're going to have to do the quadratic equation. Okay? So, since we got 2.68%, that was less than 5%, we're good. So that means that this value will satisfy our X, and we can use that as our X in this equation. So now that we have X, okay, we want to find in part 6, right, we're going to use X to get our concentration in H+, right? Remember that was step 6? So we know that we're looking for our concentration in H+ at equilibrium. It happens to be that our concentration in H+ at equilibrium is equal to X, all right, which means that this is equal to 0.0268 molar, okay? So step 7 is to calculate your pH, which is equal to the negative log base 10 of our concentration of H+, which is 0.0268 molar, okay? So that would give me a value of 1.57 for my pH. Okay? So that would be how you would calculate it for a weak acid. All right? Okay. Let's do another example. And I know it may seem like a lot of work, but it's actually kind of easy and very systematic. Like if you follow the steps, you'll find that you pick it up very, very quickly. Okay, you just have to practice it. Okay. And I know it'll be tempting to skip some of the steps at first. I recommend that you write out all the steps and you work through the problem systematically several times before you start condensing the steps. Plus, if you get in the habit of writing all the steps, you'll be in good shape for the exams and the quizzes, because I like to see all the steps, because if you make a mistake and you didn't show your work, I can't give you any of the credit. Okay? So, let's take a look at the example on slide 22. All right? We had a 0.100 molar solution of HNO2, right? That's nitrous acid, not HNO3, that would be nitric. This is HNO2, which is nitrous acid. And it has a Ka equal to 4.6 times 10 to the negative 4th. Our first question is it strong? And the answer is no, it's not a strong acid. Okay, so that means it's a weak acid. Okay, so since it's weak, that means we're going to compare our Kas, right? We know that the Ka for HNO2 is equal to 4.6 times 10 to the negative fourth. And we know that our Ka for H2O, or our Kw rather, it's a dissociation for water, that's equal to 1.0 times 10 to the negative 14th. Okay, this one is bigger, right? That's step 3, or rather, that's bigger. So I need to write my reaction. That would be step 3. The reaction for this is HNO2. It dissociates. Remember, it's weak, so the bigger arrow goes to the left. We have H plus NO2 minus. That's our dissociation. Coincidentally, our very next step is to write our ice table. Okay? Since it's to write our ice table, here. All right, I'm just going to use that line as our very first one, and I'm going to put I, C, and E here. Remember that if you have water in this process, you're just going to leave that column blank because it doesn't participate. Okay? Then what we're going to do is we're going to fill in our concentrations. So we have our initial concentration that was 0.100 molar. Here we had none to start with, right? It wasn't included. Okay, then we're going to have our change. We take our stoichiometric coefficient of 1 minus x because it's a reactant. Since we're moving on to products, it's 1 for our stoichiometric coefficient plus x, 1 plus x. All right, then we add them up. So we have 0.100 minus x. We have plus x, and we have plus x. All right, our very next step, step 5, is to write our Ka. Okay, which is our concentration of H plus to the first, concentration of NO2 minus to the first over our concentration of HNO2 to the first, okay? Which means that it's going to be equal to x squared over 0.100 minus x, all right? And that is equal to our Ka for this reaction, which was 4.6 times 10 to the negative fourth, okay? Then I'm going to try my 5% rule, okay? With the 5% rule, that means that I'm going to say that I have x squared over 0.100 because I'm going to drop that x, and I'm going to say that's approximately equal to 4.6 times 10 to the negative fourth, all right? Now, I then solve for x, which gives me an x equals 0.00678, okay? Which I am going to take 0.0, I have to check, right? Let me do this as the check. And I'm going to take my x over my initial concentration, right? So that's going to be 0.0, or times 100, right? I'm going to take 0.00678, divide that by my initial concentration of 0.100, multiply it by 100, and that will give me 0.678, which is percent, which is clearly less than 5%. So my x is good. Then I'm going to say, well, I know this is my x, right? So that satisfies my 5% rule. I'm going to then take 6 to use x to get my concentration in H plus, right? So I know that my concentration in H plus at equilibrium is equal to x in this case. It may not be, right? If we start out with a little bit of H, right, we would have something out front. So it's not always equal to just x. So keep that in mind. It's going to be my concentration of H plus in the equilibrium row. Okay, that's equal to x, which is equal to 0.00678. Okay, and then once I've got that, I can calculate my pH, which is equal to the negative log of my concentration of H plus, which is equal to, in this case, 2.17. All right, so it actually doesn't take too long to do these problems. All right, you just have to be on top of it. Okay, as you can see, I've begun to condense some of my steps, right? But they're all here, okay? So that should help. I figure that you guys probably want at least another example. This one will be of a different type of problem, okay? I have included that in the slides, and we can happily work through that in our discussion section, okay? But I want you guys to at least give it a try and have that prepared for when we talk about these in class, okay? The next thing that I want to talk about is on slide 24. Okay, and it sort of fits into this idea of weak acids and weak bases, right? So our next topic is going to be our percent dissociation. Okay, now, if you haven't done this already, you will see this in lab. Okay, so if it's a review, that's a good thing because it'll give you more practice. Okay, now, the percent dissociation is the amount of weak acid or weak base that has separated into ions. Okay, so the way that we calculate our percent dissociation is that we take the amount dissociated, we divide that by our initial concentration, and we multiply by 100. Okay, this will be an important equation. Okay, so make sure that you put that into memory. All right, so the way I usually do it is I usually say, okay, it's easier to think about it like my concentration, let's say in H plus at equilibrium, over my concentration in HA that I started with. Okay, and then I multiply that by 100. Okay, if I were doing bases, right, it would be my concentration in OH minus at equilibrium, right? That's the amount that's dissociated. And I put that over something like, let's say let's say we have magnesium hydroxide. That's MgOH2 that I started with, okay? So it's whatever is dissociated over whatever we started with. And then we multiply that by 100, okay? So if we're on slide 25, let's do an example, right? Here, let's calculate our percent dissociation. Okay, sometimes this is called your percent ionization. All right, so we'll calculate our percent dissociation of 0.500 molar acetic acid with a Ka equal to 1.8 times 10 to the negative fifth. Okay, now for this, I like to write HA for convenience, right? Instead of writing my H and then having my molecule for the acetate, okay? Because that's a lot of writing. Okay, so for convenience, right? The first thing that we do is we set up an ice table. If we're doing a percent dissociation problem, we are going to set up an ice table. So the very first thing in this is we write our dissociation reaction. We know it's a weak acid, so our big arrow goes to the left. We have H plus and A minus, I, C, E. Draw our table. Okay, now we have our initial concentration of acetic acid, 0.500 molar. We know that these are going to be 0 because they're not included in the problem statement. Then we do our change, right? We have 1 times negative x, 1 times positive x, and 1 times positive x, which gives us 0.5 minus x. We have an x and an x. Okay, so that's step 1. Step 2 is to write your Ka. All right, seeing some similarities, I hope. So we have that the Ka is equal to products over reactants. We have x to the first times x all over 0.5 minus x. Okay, I'm going to use my 5% rule. Okay, and this is equal to, where's my K? 1.8 times 10 to the negative fifth, right? I'm going to use my 5% rule. And solve for x, right? Now, that'll be step 3. So when I do this, right, I will have x squared over 0.5 is approximately equal to 1.8 times 10 to the negative fifth. Solving for x is equal to 0.003. Okay, then I need to check, right? So I know that my value of x is 0.003. I take my x and I put it over my initial concentration. So x over initial concentration, that's equal to, well, I need to multiply that by 100 also. That is equal to 0.003 all over 0.5 times 100, which is equal to 0.6%, which is less than 5%. So we're good. So since that is less than 5%, I know that my value of x is good. So I'm going to take my 0.003, and then I'm going to solve for my concentration in H+. So solve for the concentration in H+ at equilibrium, right? So I'm going to go to my H+, go to my equilibrium row. That happens to be x, which is going to be equal to 0.003 molar, right? So I've got my concentration in H+ at equilibrium. Now, I need to solve for my percent dissociation, all right, which is my concentration in H+ at equilibrium over my concentration in HA, initially times 100, okay? And that would be equal to 0.003 over 0.5 times 100, which is equal to 0.600% dissociation. All right, you have to say percent dissociation. Okay? So not bad. All right? Now, at this point, I'm going to stop and we will continue in our next video.